Now let's talk about motion of a point charge in a uniform electric field. We know that electric fields are caused by charges. What if you have a uniform electric field and you put a point particle inside there and see what happens? So a region of space with a uniform electric field, if you put a charged particle like here, what will happen to it? Well, number one, we know that it will experience a force, and that force will either be in the direction of the field or against the direction of the E field, depending on the charge itself. So in this case, we know that if it's along the direction of the E field, it is a positive charge, right? Because it's repelling away from the positive and going towards the negative. Newton's second law, we've talked about this in the last movie, acceleration will be given by QE over m, because the only force, as we know, that is acting on this charged particle is the electric field. Now let's do an example. A cathode ray tube is used to accelerate electrons in some TVs, computer monitors, oscilloscopes, X-ray tubes. Electrons from a heated filament pass through a hole in the cathode. They are then accelerated by an electric field between the cathode and anode. Suppose the electron passes through the hole in the cathode at a velocity 1 × 10⁵ meters per second towards the anode. Electric field between the anode and cathode is uniform and has a magnitude of 1 × 10⁴ meters per second. We need to calculate what is the acceleration of the electron, and if the anode and cathode are separated by 2 centimeters, what is the final velocity of the electron? So a cathode ray tube sort of looks like this. So this is where the TV screen is. This is where the heated filament is. This is where the anode is. This is where the cathode is. And it's basically accelerating over here. Okay? So the electrical field is going to go from the anode to the cathode. So the direction of the E field is going to be here. It is going to have electrons which are ejected. So we know that the electrons would want to move towards the anode because they're negatively charged. And it says that these have a velocity of 1 × 10⁵ meters per second. E field is 1 × 10⁴ newtons per coulomb. And the separation between the plates is 0.02 meters, okay, to centimeters. Now what does it want us to do? It wants us to find the acceleration of the electron. In order to do that, I know that the only force that's acting on this is the electrical force. This means MA equals QE. This means A equals QE over M. Again, I know charge on an electron is E. I know the mass of an electron. I know the electrical field. Just plug in the values and I get 1.76 × 10⁵ meters per second squared. So I'm just looking at the magnitude right now. Okay? Actually, if you were not looking at the magnitude, the E will be negative, so you will get acceleration negative. And all that means is that these electrons will be accelerating opposite to the direction of the E field, which you can see here. So E field goes this way, and the electrons get accelerated the other way. Part B, it asks us, what is the final velocity of the electron? So we have to find final velocity. Okay? We go back to intro 1. What do we know? We know Vf squared minus V naught squared equals 2a delta x. Okay? Vf is what we're looking for. V naught is given, which is 1 × 10⁵ meters per second squared. 2 × 1.76 × 10⁵ acceleration times delta x is this distance that it travels, which is 0.02. 0.02. Okay? Just plug in the numbers, calculate for it. So VF is going to come out to be 8.4 times 10 to the 6 meters per second. Okay? So far we've talked about an electron or a particle projected along the direction of the E field. What if this is now projected perpendicular to the field? What happens in that case? So in this example, an electron is projected horizontally into a uniform electric field directed vertically downwards between two parallel plates. The plates are 2 centimeters apart and are length 4 centimeters. The initial speed of the electron is given. As it enters the region between the plates, the electron just misses the upper plates. What is the magnitude of the electrical field? So here's an interesting problem. It says that the field is directed downwards. What does that mean? If my field is directed downwards, that means my field is this way. Charge at the top will be positive, and the charge at the bottom will be negative. And my electron is projected inside here. And it says it is in the center, and it is just going to miss the top plate. So basically, it is going to deflect that way. Okay? And initial velocity, as it is given, is 8 times 10 to the 6 meters per second along the x-axis. So I'm just going to assume x and y, just the normal coordinates, right? And it's in the middle. So that means if the total distance between here and here is 2 centimeters, this would be 1 centimeter displacement. And it also tells me that this is going to be 4 centimeters. Okay? Now, this is an electron. So the force on the electron has to be upwards, right? Has to be upwards. It is going to be deflected upwards, and it's going to just miss the plates up here. Okay? Now, what do I need? What does it want me to find? It wants me to find E. Okay? How do I find E? Well, I will start with what I know. Sigma F is equals to electric force only. We're not concerned about gravitational force or any other kind of forces. So this is the only force we are going to be concerned about. So I get MAY is equals to QE. Why AY? Because it's being deflected upwards, and the electrical field is only in the y direction. So I'm only concerned about this one right now. Okay? So this would give me E equals MAY over Q. Okay? Since this is an electron, I know the mass of the electron and I know Q. Unfortunately, I don't know A. Okay, but can I find A? And the answer is yes, probably. So AY is my next problem. I don't know what AY is. But I do know that initial velocity is along the x-axis. So I know that the initial velocity along the y-axis is 0 by default because it's only projected along the x-axis. So I can use that. Delta y is v naught y delta t plus 1/2 at squared. That will help me solve ay, right? Okay, so this goes to 0. Delta y, I know it is going to be 1 centimeter, so this is going to be 0.01 meter, right? That's how far it went up. My problem is I don't know delta t, so it'll be 1/2 ay delta t squared. Is there a way to find delta t? If I can find delta t, I can find ay. This is sort of like that projectile problem. So, projectile problem. Not really, but it is similar to a projectile problem. What do I know about projectile problems? I know that initial velocity is constant in a projectile. That means v1x does not change as the projectile moves, but v1y does change. So I can use vx equals delta x over delta t. Vx is the same as v0x, which is the same as delta x over delta t. What is delta x? How far did it travel? It travels 4 centimeters. I know v0x, which doesn't change during the whole projectile, so I can use delta t equals delta x over v0x as my problem. 0.04 meters divided by v0x, which it gives me 8 times 10 to the power 6 meters per second. That's going to be a tiny, tiny, tiny number. So delta t is of the order of 5 nanoseconds. So it travels this distance in 5 nanoseconds, which sort of makes sense, right? So once I have that, I can plug that back in here, and I can calculate AY, which I calculate to be that. Please recheck. Once I have that, I can plug it into here. Knowing M and Q, all I have to do is place values in here, and I get 4.55 times 10 to the 3 newtons per coulomb.